All right, so in the last lecture, I gave you an introduction into, let's say, the mental model that we have with MPI and the kind of functions that you call and how they work. What I would like to do in this lecture is that I give you an overview into how to debug MPI programs. When you think about debugging programs, it's of course difficult enough to debug single-threaded programs. If you have this in parallel with MPI, it turns out that debugging MPI programs is something that I can only say as it sucks. There's really no other way to put it. The primary reason for this is that there are no free parallel debuggers. There's no tools like the Eclipse debugger, for example, that helps you with this. There is a commercial tool that is called TotalView that helps. It's very expensive, but most of our work happens on free software, and there is no free software equivalent of TotalView. There are some tools that are in the pipeline that might be coming out in the next few years. In particular, there's an Eclipse project that is called the Parallel Tools Project, PTP, or Parallel Tool Platform, PTP, that might make this a lot simpler, but for the time being, there is nothing that really can help you with this. So what I would like to do in this lecture is that at least I show you some of the common sources of errors. One of the things that turns out is when you want to debug MPI programs, you really have to have, let's say, an experience in what kind of problems you typically encounter. It's very easy to confuse yourself because you don't just have to look at one program, but you have to look at all of the other programs in this world as well, or in your MPI universe as well. And the situation that you find yourself in one program does not typically help you understand how you got there. You actually need to look at the other programs as well that are running at the same time to understand how you got into this mess on one processor and what the correct solution would be. It turns out that there's a relatively small number of common mistakes that we make. And so what I would like to do in this lecture is that I give you an example of a deadlock. A deadlock is a situation where all processors are waiting for something and then nothing happens. In particular, no computations that you wanted to have happen, and the program never terminates itself either. And the other one is a situation where it looks like one function takes a long time, but in reality, that's not the case. So in both of these cases, it's essential that you have, let's say, that you know what common sources of errors are, so that you can map what you see in the debugger or through printf statements or however you want to debug this problem, so that you can map whatever you see there with let's say your collection of typical errors, and that helps you to find the problem. Okay, so let me look at deadlocks first. So a deadlock is I should also say this. So there is a significant amount of information in the deal.II frequently asked questions that walks you some of this information in addition to what I'm going to say here. So a deadlock informally can be described as the program hangs. So the program simply doesn't move. It seems to be waiting for something. It doesn't compute anything useful. It also never terminates. It never terminates. Formally, it's a situation in which two or more competing actions are each waiting for the other to finish, and neither ever does. So as an example is, let's say, if I gave you the example of a mail service, if I'm waiting for a letter, but my neighbor, who I expect the letter to send the letter, is also waiting for something from me, then we're both standing at our mailbox, and nothing ever comes in. We wait for the mailman. The mailman comes and goes, but doesn't deliver a letter. And that situation will continue forever because both I am waiting and my neighbor is waiting instead of one of us writing a letter. If the other person was writing a letter and would send it to me, then I could take the letter, go back, do something, send a reply, and send it back to him. But because my neighbor is waiting for something from me right now, nothing is happening. We're both standing out there, nothing is happening. So a typical example of a deadlock would be something like this. So the example is a little bit contrived, but nevertheless, I'll show it to you. So let's say we have a situation where each process has two items to work on, item 0 and item 1. And it does, so we both start with working on item 0, and then we ask the time, has the runtime already exceeded the expected runtime of a sample? If that is not the case, then we do work on the other one, and while there is still time left over, we're quite happy to receive another item from somebody else to work on this. On the other hand, if the runtime has exceeded the expected runtime, then we're just going to send our own item to somebody else who may have capacity to do it. Now, imagine the situation where both processors find that working on their item 0 already exceeded the expected runtime. Okay? So in that case, both of these send their item and are done. Right? That means that none of the processes items 1 are actually worked on. On the other hand, if both of these processors find that their runtime has not exceeded the runtime, they both work on the item 1, and then they get in here, for example, where then they both wait for items to arrive. And they will wait there forever, because MPI receive only returns when an item has actually been received. So what we get is a situation where all processors may end up waiting for incoming message in the same place, and nobody moves. That means the program hangs. And so if you wanted to debug this, you would need to find out where is each one of these MPI processes and why are they there? Why are they all in the same place waiting? So in order to show this to you, I'm going to run this program. So I just showed you the outline of the program. I have a completed version here. So I have a function doWork that essentially just prints that this processor is working on this particular item. And then in main, we initialize MPI here. We ask what is our own rank. And then processor 0 is going to work on items 1 and 2, and processor 1 is going to work on items 3 and 4. And then the rest of the code looks like I just showed you, with the difference that the initial time expired. So the first condition, I assume that we have always exceeded the expected time for working on one item. So in practice, of course, you would make this more elaborate, but in order to demonstrate how this happens here, I'm going to set this always to true. So we're going to work, each of the processors is going to work on item 0, and then we go into this place here where we send the items, and then while there is still time, which we assume is always the case, we wait for items to be received, and then we work on them. So each one of these processors here will send its second item, will receive something from the other processor, and then, well, get into the receive again a second time. Okay, so if I compile this program with MPI capital CC minus O, so I'm going to write the result, the executable, into this program, into the file called deadlock, and I'm going to compile deadlock.cc. So I'm going to do this, and then I'm going to run the program. MPI run minus np2 ./deadlock means I'm going to take this executable ./deadlock, and I'm going to run it with 2 processors, minus np2. So in my case, they're going to run on different cores on my laptop, but if this was a cluster, they might be distributed to two different nodes. So if I do this, then processor 0 is going to say it's working on item 1, then it sent item number 2 to the other processor. Okay. Processor 1 was working on 3 and had sent 4 to processor 0, so 0 is also waiting for item number, or is working on item 4, and then nothing happens. Okay, so the program in particular does not abort, it doesn't terminate, it doesn't ever seem to do anything. That's a typical situation of a deadlock. Okay, so I can see if I call top that indeed there are 2 instances of this program, and as a matter of fact, they're running full steam here. That's because MPI receive essentially just keeps asking, is there a message, is there a message, is there a message, is there a message? There is never any message, but it keeps asking. So they both take 100% of one core on my machine. So if I wanted to understand what is going on here, I need to find out where exactly these two processors hang. And like I said, in the absence of any particularly good tool to show what is happening here, I'm going to show you the poor man's version of this. The poor man's version works by calling each one of these programs in a debugger. So I'm going to do the following. So instead of just running this process./deadlock on two different, let's say on two different processes, what I'm going to do is I'm going to tell MPI run to just open two extern windows, okay? And in each one of these extern windows, I ask, please execute GDB, that's the GNU debugger, and the GNU debugger should please run on the executable deadlock. Okay, so I get two windows here. And in the following, so I can't adjust the font size in Xterm, but if you watch this on YouTube, at the bottom right of the YouTube window, there is a gear symbol. You can click on that, and you can go to high resolution, and then you should be able to see this. So I have two windows, each of which is running a GDB instance, each of which GDBs is running my program deadlock. All right, let's say at the beginning it is just it is stopped at the top of main. But I can say run in each of these windows, okay? And you see over here on the right that nothing is moving right now because MPI programs have to call MPI init at the very top, and MPI init only returns when all programs have checked in. So it's like a barrier. So once I type run in the left window, both of these programs will start running, okay? So processor 0 has output something here, and processor 1 has output something over here, okay? And now they both hang. So in order to find out where they hang, I'm going to abort both of these in GDB, and I do this with Control-C, okay? Control-C. And then let me see where I actually am in this program. So I type in backtrace in both windows, okay? Backtrace. That's essentially the command that Eclipse also does when we show at the backtrace in the Eclipse window. You've seen this in one of the earlier lessons. So what it shows me is that right now I am in something that is called frame 0. That is a function for which GDB cannot determine the name of the function, and it is somewhere in the open MPI implementation. I don't really actually care where that is. I need to find my way up to a place where I recognize something. So this place was called by a function that was called opal progress, which was itself called by a function whose name cannot be determined, which was itself called by a function that is called MPI receive, which is a synonym for MPI receive, which was itself called by a function called main. Well, that's of course where the problem happened. So I know that I know the call stack. I know how I got where I am. Now I need to see which line does this correspond to. So what I will do is I will go to frame 4, for example. Okay, that's in the main function, and then I can type list. So if this was a graphical debugger, when I click on frame 4, it would automatically jump in the code to the location where that is. But in, let's say, this command line interface, at least I can say list, and it's going to say, that is not what I intended to happen. Yes, it doesn't show me any line of code because I didn't compile the program with debug information. So let me do this whole thing again. I say quit, gets out here. So I need to compile my program with MPICC -G deadlock. That's a common mistake. So I'm going to run this whole thing again. Back here, I say run. I say run. It outputs something. It hangs. I abort it, or I stop it here. I say back trace in both of these windows. Back trace again in main, which called PMPI receive, and so on and so forth. I go into frame 4. Okay. Now it tells me that I'm in line 46 of deadlock.cc. So I can get some context by saying list, and When I do this, then it shows me the whole code block here. So line 46 is exactly the location where I expected it to be. So now I know where it is on one of the MPI processes. Okay, in the other MPI process, it is in a place called opal progress, called from an unknown function, called from PMPI receive, called from main. Apparently, so you see that these two programs are in different places, right? Here in this window over here, I saw that main is frame number 4, and it had called 3 other functions, whereas here main is frame number 3, and 4, and had called 4 other functions. Here it is frame number 3 and had called 3 other functions. So you see that not all programs must always be in exactly the same location. Now, here I go into frame 3, I say list. It turns out, of course, it is the same location here. So they both are stopped in line 46. And we have already understood why that is so. I explained it to you already. But the point is that one of the things that you always need to find out is if you have a deadlock is where exactly you are. And not just where you are in one of the processes, but you need to understand where they all are. And this example here with running GDB in 2 different windows is sort of the simplest way of finding this out. You could do this with printf or writing something to see out, of course, but that is the simplest way of doing it. Once you know why you are where you are, it actually turns out to be fairly trivial to figure out oftentimes how you got there. If you have sort of a mental model of what your program does, that's the next step that you then have to take. Once you know where you are, you need to figure out why, and that's the easier step. So I'm not going to show you how to fix this program here. The program doesn't do anything useful. There's no point in fixing it. But I wanted you to understand, let's say, at least one of the tools how you can find out where exactly we are. All right, so with this, I want to give you a second example of a deadlock. So a deadlock can also look like this. And that turns out to be maybe one of the more, so the first one was clearly a wrongly designed algorithm. Here is something that can happen sort of by accident. So let's say I have a function f, and it computes something locally. And then we have an if statement that says, well, you know, if I need to, or do I need to sum all of the results that we have computed locally into one global number? If so, I allocate an integer called sum, and I'm going to call MPI reduce. That is going to take the integer here, put it into sum. There's only one integer, data type MPI int. The operation is MPI sum. When we're done with this, we're going to compute something else, and then we add up all of the k's, or the k's. Okay. Imagine the situation where this function need to sum returns true for processor 0 and false for processor 1. Okay. What that's going to do is that processor 0 goes into this block and is going to call MPI reduce, okay, whereas processor 1 is going to jump straight over it and is going to go into this MPI reduce. And if you get really unlucky, then what is going to happen is that processor 1 is going to send its variable kk, processor 0 is going to think that that is going to participate in this particular reduction operation and is going to add it up. But in any case, when processor 0 gets to this place here, processor 1 has already passed that place and isn't sending anything. So processor 1 will already have left that function, okay, and processor 0 is going to wait forever because there's no more data coming in. So again, we're in a situation where you end up with a deadlock. Okay. So to show you this example again, let me go out of these debuggers here. I have a second program that is called deadlock.II, okay, which implements exactly this. So I have a function foo that returns 1, a function bar that returns 1. This function need to sum returns either yes or no, depending on whether I'm on processor 0 or processor 1. okay? And then, like I showed you before, right? So I have this if statement here, which means that only one of the processors goes in there, okay? And we're going to call this MPI reduce, this MPI reduce here from only one processor, and this one we would like to call from both processors, okay? So if I compile this program the same way as I had done before, so I'm going to call MPI cc minus g minus o deadlock2 deadlock2.cc. If I simply execute this, then I'm going to get an error message here, okay? In this case, the MPI implementation has figured out that we get to the second MPI reduce call, but only one of the processors participates and the other one has already left, okay? So I must admit that I don't quite know whether I can debug this in GDB, but let us try. Okay, so here it says starting on rank 0, summing on rank 0, but here it says only starting on rank 1, right? And so we're again left in a situation where the program seems to hang. So let me abort this with Control-C in GDB, and then I'm going to go do a backtrace. So what you see is that for this process over here on the right, we're stopped in deadlock2.cc in line 22, whereas the one on the left here is stopped in line 27. Okay, everything below this are MPI calls. I don't care about these. So let me go to frame 6 over here and frame 6 over here as well, and do a list. Okay, so what it shows me here is that I'm stopped in line 27, so that's this MPI reduce, whereas over here on the right I'm stopped in line 22, which is this one here. Okay, so when you see the situation, you will have to figure out, okay, so obviously I'm in different places in my program. Why the heck, for example, on this left window here, did it already make its way down here to the second MPI reduce, when in the other program over here it is still stopped in the first one? Okay, and then you work your way back in the program and you try to figure out why did we get into this if block here but not on the other processor. So that's sort of the process of trying to figure out how that works. The point I want to make is that if you look at only one of these two programs, there is nothing you can do. There is no information that tells you what is wrong, right? I mean, both of these function calls to MPI reduce look perfectly innocent. They look like they're doing the right thing. The only way to figure out why the program hangs is if you find out that the program is in different places on different processes. So it is imperative for you to find out where you are in your program, or you will not be able to find out what is wrong with the program. Okay, here's the last example that I would like to talk about, namely, how long does an operation take? So oftentimes we want to time how long an operation takes, and here's an example. So let's say I have a timer t, I start it, I call a function my function, and I stop it, and then if I'm on processor 0, I'm going to say this took so and so many seconds. So these are deal.II classes, timer, t.start and t.end, and timer parenthesis means just give me the number of seconds between the previous start and stop. So the idea, of course, here is that I want to measure how long this function my function takes, right? So I need to figure out, let's say here, which may be a function that does some MPI communication, how many seconds between we started it and we stopped it. Oftentimes what you find if you do this, and if you don't do it right, is that you get results that don't seem to make any sense. So imagine, for example, the following situation. We're in a bigger context here, where this function, my function, does the following. So it computes something locally, okay? Then it computes a reduction operation, and on processor 0, for example, is going to output the result of the reduction operation. If this computes something locally, is quick on processor 0 but takes long on processor 1, then processor 0 will immediately jump over this here and will go into MPI reduce, and then it's going to hang for a very long time in MPI reduce until processor 1 actually participates in the MPI reduce. Okay? So you would erroneously have to conclude that my function takes long because compute something locally might have taken long on processor 0, when in reality all we did was waiting for processor 1 for the MPI reduce. So here's the graphical depiction, and I would like you to ignore what we have done here. So let's say we're on processor 0 and 1. We have something going on here. Both of them, for example, happen to start my function quickly. Okay, but then the local computation is quick on processor 0 and takes a long time on processor 1. Processor 0 therefore goes quickly into MPI reduce, but then you wait in MPI reduce until finally processor 1 sends the data over here. Okay, so what that time between start and end is this entire time interval here that measures how long it took me to do my function from start to end. And what it's going to say is going to take a long time, when in reality we spent almost all our time waiting for something on processor 1. Now remember, we called this on processor 0. So on processor 0, we're going to learn that it's taking a long time to call that function, when the problem really was that processor 1 took a long time. Here's another situation. So let me assume, for example, that I have the same sort of situation, and that on both functions actually my function takes the same amount of time. In particular, the local computation takes the same amount of time. But imagine, for example, that everything that happened before my function took a lot longer on processor 1 than on processor 0. Okay, so you might end up with a situation that would look like this. So something long is happening here, something short is happening here before my function on processor 0, but it takes a lot longer to do on processor 1. And then we do some local computation that takes exactly as long on processor 0 as in processor 1. Okay? But because processor 0 started a lot earlier, it gets into this MPI reduce at a time when processor 1 hasn't even started my function yet. So only when they finally get both together and exchange data here can processor 0 continue to work. So again, what you will get to see is that processor 0 seems to take a very long time in this function here, when that is in fact not at all the case. It's a fairly quick function, and it takes the actual compute time, the blue pieces here, takes exactly as long on the on processor 0 as in processor 1. Now, the point I want to make is that just because something takes long doesn't mean that either processor 0 or processor 1 actually takes a long time. It might very well be that on processor 1, the previous operation took a long time. And so in order to rule this out, the only way you can avoid that, that erroneous conclusion is if you put a barrier at the beginning of your timing operation, that before you start your timer, you need to have a barrier where everybody checks in and says, yes, I'm here, I'm going to start working on my function now, okay? And then you actually time. So that will give you then the maximum of the times between all of the processors. So the point really here is that it's often difficult to evaluate which it is. If it really is that the function takes a long time, or if it is that something completely different is happening. And you have to keep an open mind, and you have to have the techniques and the strategies to figure this out. So, like I said, there is a lot more material that explains these sort of things and the techniques on the deal.II frequently asked questions that shows you how to deal with this. So to sum this up, parallel computations may present riddles to you that are very difficult to understand, that you can spend a lot of time looking in the wrong place, and that in order to figure out how to what is going on, you need to have sort of a familiarity with common patterns of mistakes. And then one of the things that is useful to learn is how to run debuggers on parallel programs. And with that, I'll leave it for this class here.